This lecture is going to be about earthquakes again, part 2 of earthquakes here. For the purposes of this lecture, we're going to talk about the types of seismic waves, and then we'll talk about what magnitude and intensity are. All right, so anytime an earthquake happens, the actual shaking that is felt, what you're feeling is seismic waves, which is a form of energy that is created when an earthquake happens. So we already established some definitions. An earthquake occurs on a fault. The earthquake starts at the focus, and then if you draw a line straight up from the focus vertically, that's where the epicenter is. So when we're looking at this diagram, where the earthquake happens again is the focus, and then the yellow circles that you see, that's energy or seismic waves that will radiate outward from the focus. And when they reach the surface, that's what creates the shaking that people feel on the surface. So that's called seismic waves. There's different types of motion that's associated with seismic waves. And we can record that shaking on something called a seismograph, which basically just has a needle with ink in the old-fashioned times that just moves back and forth when the ground is shaking when an earthquake occurs. Just to show you this animation. So what this is going to show you is how seismic waves can travel through Earth's interior and then around the surface. So we have the globe here basically, and the earthquake is happening on the left side. And then the yellow and red and blue and green colors that you see, it's basically showing you how seismic waves or shaking can travel all the way across the globe. So they can go through Earth's mantle, outer core, inner core, and then they can be detected on the opposite side of Earth. So if I play this through again, just to show you, the earthquake starts on the left side here, the red and yellow, and then the blue and green, that's indicating to you earthquake shaking. Earthquake waves, they can travel through the mantle, the outer core, the inner core, and back out the other side of Earth. So let's talk about these seismic waves. There's different types of motion or different types of energy that occur when an earthquake happens. Let's say you go to Japan at some point and you experience an earthquake. Depending on where you are in location to the epicenter of that earthquake, you're going to feel 4 different types of shaking in a sequence, a very predictable sequence, and they follow primary waves first, then secondary, then something called a Rayleigh wave, and then something called a Love wave. So when we're looking at the difference between these body waves, these are waves that can travel through Earth's interior. So they can go through their kind of our red colors and blue colors here. They can go through the mantle, they can go through the core, and they can travel through the interior of Earth. So we call it the body waves because they go through interior of Earth. There's also surface waves, which are our R and L waves. Those are the yellow squiggles here that we can see that they travel on Earth's surface. So for each of these, they have their own kind of motion that we'll talk about here in a second in terms of how they, what they do to Earth's surface. So let's start with the first two. These are the body waves. So there's 2 types. There's primary waves and then secondary waves. Primary waves always show up first. So an earthquake would happen. You're in a skyscraper in Tokyo. Primary wave shows up first, and what it does is it compresses materials. So it will either lead to like a shortening of material or a lengthening of material based on this diagram here on the right side. And I'll show you animations of this in a second. Secondary waves have an up and down motion, almost like a roller coaster, so up and down motion. That is what a secondary wave is. So primary wave shows up. Maybe that shaking happens for 30 seconds or so. It's compressing the ground. And then another 30 seconds will pass, and then the secondary wave shows up. Ground will shake. And then it's not done. But I have your first quiz question here. So you got to do a little math. Primary waves travel through Earth's interior at a speed of up to 14 kilometers per second. Translating that to miles per hour, it's about 30,000 miles per hour. So if the diameter of Earth is 7,900 miles, how long in minutes would it take a primary wave to travel through Earth's interior and be detected on the other side of Earth? All right, so again, if you want to pause here before you proceed, feel free to. So let's say you're in Tokyo, you feel the primary wave, you feel the secondary wave. There's still 2 more waves that are coming that would hit the location where you are. Those are what we call the Rayleigh wave, which is shortened to R, and then the Love wave, which is shortened to the L wave. So these only travel on the surface, but they cause most of the damage, and that's because they have the most severe type of shaking. So a Rayleigh wave is kind of like a rolling ocean wave. So if you can picture like a breaking wave coming in at the ocean front, you have this wave that comes in and then it kind of rolls over and breaks as it does so. The ground would follow that same kind of motion, so it'll roll and kind of topple over, which I know is kind of hard to think of the ground actually doing that, but that's what a Rayleigh wave does. And then a love wave is the last type, and it's basically a snake-like motion, so it moves side to side like a snake. So primary wave first, compression. Secondary wave second, you get an up and down motion. Rayleigh wave, you get a rolling motion. And then a love wave, you get a snake-like motion. So for 100% of earthquakes, all 4 of those types of waves are generated. All 4 of those types of motion of shaking are generated. All right, so here's some just animations to show you kind of the propagation of those waves. The primary wave is on the top. If you look at kind of the black box in the center here, it'll show you what a foundation of a building would do in response to an earthquake hitting it. So that's our compression wave. Secondary wave's got that up and down motion. So if you watch the box, up and down motion. Then I got love wave, snake-like side to side motion. And then the Rayleigh wave is kind of like, again, a rolling ocean wave. So all 4 of these waves hit. They all have different types of motion associated with them. All right, just to show you what that would do to a hypothetical roadway with some power lines, the primary wave would compress and break the road into different blocks. The S wave would make it roll or move up and down. The love wave is that snake-like motion, so those broken blocks would now shift in different directions. And then the Rayleigh wave, again, would have that kind of rolling ocean wave that passes through it. All right, so based on what we just talked about, you could use the diagram below to answer questions 2 and 3 on the quiz, and then feel free to return once you've answered those questions. All right, so every time an earthquake happens, as I said, all of those waves are generated. They're going to show up in sequence, primary first, secondary second, and then we lump L and R together into surface waves. So this is a seismogram. It's basically showing you at times, so time is on the x-axis, and at time 0, that's always when the earthquake happens. So earthquake happens, and then a little bit of time will pass before that energy or those waves travel to a location. Then the primary wave shows up, then the secondary wave shows up, and then the surface wave shows up. So these are color-coded just to show you which different type of wave occurs. Now, this location on the right side would be a little bit farther away. This is time. Earthquake happens right here. Time will pass before the primary wave shows up, then the secondary wave, then the surface wave. But again, it follows that same sequence, primary, secondary, surface. All right, so based on that, you have this question here. So you have a seismogram which shows you when different seismic waves arrive. What I want you to do is kind of use this figure from the last slide to interpret the secondary wave when it shows up. That's your blue color. And then use that to interpret which letter corresponds to the secondary wave arrival in this diagram. What I also want to point out about earthquakes is that the closer you are to the epicenter, the more shaking you feel. The farther you are from the epicenter, the less shaking that you feel. So for example, if this red diamond is the epicenter of a 1994 earthquake in California, Pasadena was the closest to it, so it felt the earthquake first, and it also had the most intense shaking because it was the closest to the epicenter. So for example, that earthquake only took 7 seconds to travel to Pasadena. Goldstone, which is 122 miles away, it took 35 seconds for the earthquake waves to travel to that location. And then Needles is 220 miles away, less shaking, but it took a full minute for it to get to that location. So based on that, if we move the hypothetical epicenter to the star here, which location felt the earthquake first now? Then lastly, you can answer question 6 when you're looking at this diagram here. Moving on to the second part of our lecture here, we're just going to talk about measuring earthquakes really quickly. Magnitude is how we measure earthquakes. So you might have heard when they talk about earthquakes on the news, they're going to say it was a magnitude 7 or magnitude 8. So we're going to talk about what that means. The technical definition of a magnitude is the energy released from earthquakes. So an example of this is that you could take a 40-watt bulb and a 100-watt bulb. The 100-watt bulb is brighter, but it's using more energy. A higher magnitude earthquake has more energy associated with it. So earthquake magnitude scale, the smaller the earthquake, the less bad it is. The higher the magnitude, the more bad it is. So usually an 8 or greater is considered a great earthquake, and that has the potential to destroy everything, entire communities, entire cities, because of its strength or the energy released from it. So how the earthquake magnitude scale works is that every number that you go up, this is what we call a log scale. So a log scale means that you increase by a power of 10 as you go up in order in number. So as an example, each increase in number is a 10 times increase in strength or energy released. So just to give an example, a magnitude 7 earthquake is 10 times stronger than a magnitude 6 earthquake. Or you could phrase that as a magnitude 6 earthquake is 10 times weaker than a magnitude 7 earthquake. All right, so that's how log scale works. Again, every order you go up, or every number you go up, you're increasing or decreasing magnitude by 10 times. All right, so the larger the earthquake, the more destructive it tends to be. What this figure is showing you is that on average, we have a bunch more earthquakes that are lower magnitude, like 2 and 3 each year, more than 1 million. But once you get up to the 8s and 9s, it's about 4 of those per year, but really just one big earthquake or less than one earthquake every magnitude 9 earthquake every year. So there's been a couple that have been quite large, greater than a 9. There was an Alaska earthquake in 1964. That was a 9.1, and then the largest earthquake ever recorded was in Chile in 1960, and that was a 9.4, I believe. All right, again, just to show you a comparison of log scale. So if you have a magnitude 6.1 compared to a 7.7, a 7 is 10 times greater than a 6. So what we're seeing here is the difference in relative proportions of shaking that would occur comparing a 6.1 to a 7.7. So larger magnitude due to log scale is going to be much more powerful than a smaller magnitude. All right, so based on that, you have questions 7 and 8. So how many times more powerful is a magnitude 9 relative to a magnitude 7? And then how many times weaker is a magnitude 4 earthquake relative to a magnitude 7 earthquake? Finally, a second way that we measure earthquakes, in addition to magnitude, is their intensity. So intensity is a qualitative measure, so it's descriptive. It doesn't have numbers associated with it, but it's telling you what kind of damage was done. So typically when an earthquake happens, geologists are going to determine the magnitude and the intensity. Magnitude does not change. Intensity changes by location. So intensity is looking at damage to people, damage to buildings, damage to infrastructure, and it's measured on this scale called the Mercalli Intensity Scale. So the Mercalli Intensity Scale is ranked from category 1 to category 12. Here's an image of the scale. 1 means it's not felt by people. 2 is that it's just perceptible, and maybe upper floors of tall buildings, you can feel the building shake a little bit. But as you go up in category, it becomes more disastrous, all the way up to what is called a catastrophic 1. So catastrophic would be something that has total destruction of an entire city. It has objects thrown into the air. Rivers reverse direction, and you can alter the landscape. So it either, maybe the land surface has been crumpled and pushed up by 50 feet, 100 feet. So it basically just like resets the land surface in a catastrophic intensity. So most earthquakes fall somewhere in between categories. We have very few earthquakes that have been considered catastrophic. Okay, so you should have a quiz question associated with looking at the Mercalli scale and deciding on the intensity. Same thing here. If you're still trying to answer the quiz question, this kind of shows you a comparison of what the different categories would do to a potential town or landscape. Higher category is going to level basically all the buildings. All right, and then just to show you kind of an animation, this is from 1906. So this is a magnitude 7.8. The magnitude 7.8 earthquake doesn't change. But in San Francisco, what you're seeing here basically is 10 seconds after the earthquake occurred. The red colors indicate the higher intensity, so the more intense shaking. Blue indicates less intense shaking. So the point here is that the magnitude is 7.8 regardless. Shaking intensity changes depending on the location. So closer to the epicenter, more intense shaking. Farther from the epicenter, less intense shaking. All right, there's a link to a video that you'll have to watch for another quiz question. So that's here for you, but it's also on the quiz. And then lastly, you're going to complete the quiz and then there's a homework assignment associated with this lecture. You're going to need to use the Mercalli intensity table and scale to complete this homework. And I've put that homework on Blackboard in the earthquake section.